Now, let's talk about stresses in an inclined plane. For that, I'm going to bring our peanut-shaped body that we draw at the beginning of this lesson or this topic. It's going to be something like this. At that time, let's say that we assume that the force coming out of the point we decided that we chose on the body was normal to the cut plane. But in this case, what we're going to assume, or the main deal of this topic, is to know how to calculate a stress on a different plane, or on a plane that is oriented differently to our Cartesian coordinate system. I'm going to draw the same force here. Call it this time T. And the other plane, or this inclined plane, is going to have two main vectors that are going to define the plane. As we have been using this convention of normal stresses and shear stresses, I'm going to draw here the same convention. I'm going to have a plane here, small plane, and from it, two unit vectors I'm going to come out of that, from that. So it's going to be this normal vector. And I'm going to have a tangential vector that I'm going to represent with the same sign of the, or symbol of the shear stress. So how to represent this stress T in this other coordinate system? Starting from our Cartesian coordinate system, X, Y, Z, to the new coordinate system. That's why we need to define here something that I mentioned in the last video that was called the direction cosines. Let me draw another helper here, another figure that is going to allow us to understand what's happening here, or how to utilize these direction cosines. I'm going to draw a Cartesian coordinate system and to draw it on the right. It's going to be something like this. And this. It's going to be my X. Fix this. Yes. Y and Z axis. And I'm going to have located a force here, or a vector. I could say that, of course, the representation of this vector F in this Cartesian coordinate system can be done through its components in each of the individual axes, X, Y, and Z. But how to calculate those individual components? I could say that this vector forms certain angles with the axis. I could say that the force forms an angle alpha with respect to the x-axis, that it forms an angle beta with respect to the y-angle, and I could say that it forms an angle theta with respect to the z-axis. Now, I could easily say that, I'm going to write it in red here, that component of F in the x-axis is going to be equal to F times the cosine of alpha. Similarly, I could say that component of F in the y, or projected onto the y-axis, is going to be equal to F times the cosine of beta. And the component of the F vector projected onto the z-axis is going to be equal to F times the cosine of theta. Yes. This segment here that I'm going to enclose in a rectangle is what is known as direction cosines. Cosines. These direction cosines, again, are formed by the different angles represent that, let's say that the vector F formed with each one of the angles of in the Cartesian coordinate system. If I could say, kind of as a matter of, to say, definition, how to represent or how to write these, understand better these direction cosines, I will draw a unit vector, again, on a Cartesian coordinate system. I will have this. So to look at it a little bit better, because I want to come up with a way to simplify the writing of these direction cosines. I will have draw it on green here. This one. A cube also. To write all in hidden lines or dashed lines. Great. And I will have my let me try to put it better because it doesn't give me the effect I wanted to have. We'll draw first this. Then from it, I will start the box. Yeah. Yes. This looks a little bit crooked. It's being a mess, but bear with me. All right. I'm going to have here these three components of this vector. Actually, I'm going to call this vector n, like this one here, unit vector n, or pointing. In this case, this vector n, unit vector n, is pointing in the normal direction to this plane. And just to represent it here equally, I want to see how this vector n can be represented in terms of the Cartesian coordinate system. And this is going to have three components here. Nx. This one here is going to be Ny. And this one here is going to be Nz. Yes. Applying the same rule that we found in here, where the vector f was defined, or the components of the vector f were defined in terms of its direction cosines, I will do the same here with this unit vector. But in this case, as it is a unit vector, the magnitude is 1, and then I don't have to write the magnitude itself. I don't have to write the 1. So we'll write that here, that nx equals to the cosine. As I haven't written any angle here between the unit vector n and the Cartesian axis, I will call it in this way, that nx is going to be defined by the cosine of the vector, unit vector n, and the axis x. And actually, I will call this as L. And y is going to be defined by the cosine of the unit vector n and the axis, Cartesian axis y. I will call this M. Finally, Nz is going to be defined by the cosine of the unit vector n and the Cartesian axis z. I'm going to call this N as a simplification name, simplified name. One important thing to consider here is that these three angles are not independent. There are two independent angles and one, let's say, dependent angles. Let me show you what I mean by that. So if I come back to the example of the force, or this vector f, not for the vector f, I can say that if I wanted to know the magnitude of the vector f, I would have to apply some equivalence of the Pythagorean theorem. And that's going to be something like this. F squared equals to the sum of the square of the components. Again, fx squared plus fy squared plus fz squared. Then I could simplify this more by taking a common factor f squared, put it in this way. F squared equals to f squared parentheses cosine of alpha. I'm substituting here what I already did in this part here. Cosine square alpha plus cosine square beta plus cosine square theta. A bit to the right. Now, I could keep simplifying this, and I would say that I can simplify this f squared and say that 1 equals to cosine square alpha plus cosine square beta plus cosine square theta. By similitude, I could say that this, in this case, could be represented as 1 equals to L squared plus M squared plus N squared. Now you see that if I have two of the angles, I could find the third angle because this equation here, actually only two angles are needed to find any of the other two. How is that? Well, if you want to find, for example, the angle between the unit vector n and the x-axis, means that I need to solve this equation for L. So this is going to be equal to L squared equal to 1 minus M squared minus N squared. And there you go. You have the solution for that. So there is only two angles that are independent in this case. Beautiful. Let's see the other part of this. If I bring down this small plane that I selected here that is oriented differently to my Cartesian coordinate system, I will end up having something like this case. I will have a plane and I will have my main orientations that are going to be the normal to that plane represented by the unit vector n, and the tangential to that vector plane represented by the unit vector tau, in this case. And again, I will have my, which color? Yeah, green. I will have my vector. Then this vector here is going to have also, it's going to represent two components here. This first here is going to be the normal vector of this tau. I will write it like, like this. And this one here, I'm going to represent it as tau. Meaning that if I know a vector in my Cartesian coordinate system, I could transform or orient that vector into another plane, which main axes are going to be the normal to the plane and the shear, one shear or tangential axis to that plane. I could say that this vector, the vectors that I already found out there, that sigma is going to be this t times the cosine of alpha, if I consider that this is alpha, and tau is going to be equal to t times the sine of alpha. Well, so why is this going to be important? Well, let's look at it right now. Just keep it in mind. Let's say that there's going to be a certain relation between these two vectors that in the end, I'm going to say that t, or that vector that I'm represented that might be a stress, it's going to be equal to the sum of the normal component plus the tangential component or tau component. Meaning that if I have any of those two terms in this equation, I would be able to find the third one. Now let's take it to a better or more illustrative case. Let's have what the name of this, let's say, topic that we're covering right now is an inclined phase or stresses in an inclined phase. What's going to happen here? I'm going to draw a Cartesian coordinate system in here. And I will draw also an inclined plane, an arbitrary inclined plane. Let's put this from here to here to here. So it's going to be something like this. Let me put it in blue. This one, and this one. Try to identify this plane. I'm going to name these 3 points with the letters A, B, and C. So let's see, this is going to be my plane. Nice. Let's locate on that plane the vector we have been working with. So we have this vector t. And this vector, as we mentioned, is going to be represented in our Cartesian coordinate system, kind of by means of tx, ty, and tz. Let's call this my area A. If I want to write it better, meaning that I want to represent this, to show how to represent this vector t into my new set of coordinate axes represented by the normal to this plane, I will draw it again. I will draw this plane again. Yes, this is going to be A, B, and C. I will have the normal to this plane represented by the unit vector n, and the tangential to this plane represented by the vector tau, unit vector tau. And I will have my vector t, this one being this one here. This is going to be, or this vector t is going to have 2 components represented on the vectors, the normal and tangential vectors here. And this is going to originate normal vector and this tau vector. Meaning that if this is a strength represented, again, this is a strength represented on my Cartesian coordinate system, x, y, z, then in another plane or on an inclined phase, this is going to produce a normal vector, which is going to be the projection of this strength onto the unit normal or unit vector n. And it's going to produce a shear, being that, or providing that this is a stress, it's going to produce a normal stress here, and it's going to produce a shear stress here, represented by these 2 components. Now I need to mention something, because if you remember from the previous videos, that whenever we try to make or try to work with the equilibrium equations, we need to sum and subtract forces, not stresses. And to get from stresses to forces, I need to multiply these stresses by the area where those stresses are applied. So meaning that I need to find certain areas here. For example, I'm going to call the origin of my coordinate system O. Then, if I draw the forces acting or the stresses acting on this system here, meaning the stresses acting on the planes that are parallel to the Cartesian coordinate axis and stresses up on the plane that is normal or is belonging to the inclined phase, I will have something like this. I need to write again or draw again another inclined phase. So we'll have this coordinate axis. We'll have my inclined plane. And let's see, in this area here, I will have the following stresses. Remember that this is kind of represents here. This is kind of the, if I had the infinitesimal cube and I just cut a little corner of that cube or put a plane through a small corner of that cube. In this case, I will have the following stresses applied to this system. The first one is going to be, well, this yellow phase. It's going to be the normal stress, sigma xx. And it's going to be also the shear stresses in that area. I'm going to have this one here and this one here. This is going to be tau xy, and this is going to be tau xz. In this other plane or semi-plane, I will have normal stress zz, but I will also have this shear stress and this shear stress. This is going to be tau zy, and this is going to be tau zx. Also in this plane here, I will have normal vector or normal stress sigma yy. I will have this shear stress and this shear stress here. This is going to be tau yz, and this is going to be tau yx. Then additionally, I will have in the inclined plane, let me represent it outside so it is better to see. This belongs to the same figure, but just not to make a mess, I will have the following stresses. Which color? This is going to be, again, this is A, B, and C. Yeah, black. Yeah, then I will have vector to put it, yeah. T, how to put it better? yeah, tx, yeah, ty, and tc. So these and these are kind of together. Kind of this is I just took this part as away from the whole system that I'm drawing here, kind of to have better visibility in here. Now, if I try to get the equilibrium equations for this piece of cube, let's put it in this way, I will have to, well, I believe I have all the stresses acting on this piece of element. And all these stresses are, let's say, represented in all of the Cartesian coordinates. And you would say, okay, now we're talking about Cartesian coordinates, but you were saying there before that you want to know what is that stress represented now on a different plane. And we will get to that, because first we need to find the equilibrium using all the stresses in the represented or acting on the element based on my Cartesian coordinates, and then I could use the direction cosines to transform that resultant stresses into, let's say, the new plane. Remember that what we know from the state of stress of a cube or a point on a body are these terms here. We know all the normal and shear stress applied or in the form of an infinitesimal cube. But then, when we make the cut, that's going to produce a different stress that we need to find out. But this is the kind of the source of information we're going to use to determine how much this T stress value is. And then from it, we can determine what the normal stress and shear stress in the specific plane is or are. Well, let's see. Then if I apply equilibrium to this system, to this element, tetrahedral element, yeah. Again, with the same convention of positive, if the vector is aligned with the positive axis of my Cartesian coordinate system, then that vector is going to be positive. In X, if I start doing this, I will have that. This is important. That's something that I was forgetting about. So I'm working with stresses, but if I calculate the equilibrium, I need to work with forces. And to work with forces, I need to know what's the value of the area, for example, the yellow area, what's the value of the blue area, and then what's the value of this kind of, I don't know what's the color, kind of purple area. Let's call it purple, even though it's not purple, kind of violet. Believe it now, but this area follow the same, let's say, rule of the direction cosines. I can explain that later. But basically what I'm going to say here is that the area represented by C, the triangle, this is A, B, C, and this is O. The area represented by the triangle C, O, B is going to be equal to the area times L. I need to make a change here. Let's call this in A, B, C better, because it's going to make a confusion with the terms. C, O, B equals to AL. And then kind of the area, the big area, this one here, change it here also. A, B, C. This is A. The inclined plane, the inclined area multiplied by the cosine direction L is going to give me this yellow area here. Then I will have COA is going to be equal to the big area times this direction cosine, and the big area, or the area parallel to my Cartesian coordinate system, AOB is going to be equal to A times the n direction cosine. You're going to see now why this is important. If I make the sum of forces in the x direction, or along the x direction, I'm going to have as positive force Tx. And Tx is applied on the big area A. And that's going to give me the force there. Then minus this normal vector here times, which is applied in the yellow area. And that's going to be sigma xx times AL minus the other one who is applied, or is say aligned with the x-axis, is yx. Tau yx is applied on the purple or violet area, and that's going to be the COA. COA is going to be A times M. And finally, the other shear stress is going to be CX AM. And this is going to be equal to 0. As definitely we're working with an area, an existing area, I can right away say that these can go away. We'll rewrite this as Tx minus sigma xxl minus tau yxm minus tau zxn equals 0. Let's work now with the y-axis. We'll try to make it in the same page. I will have that Tya, yes, minus sigma y am, yes, minus tau xy al minus, let's see, yeah, tau zx an equals 0. Again, I could get rid of this one and I can rewrite this, but while I am rewriting it, I'm going to follow the convention LMN. It's going to be Ty minus tau xyl minus sigma ym minus tau zxn equal to 0. Zy. Let me recheck this. XY. Recheck this. In the y direction, we have zy. And we have xy. Sorry, there's a mistake here. Cy. Cy. Yes. Good. Then in the z-axis, I'm going to have dz times a minus, let's see, z-axis. Who is applying on the z-axis? Oh, definitely sigma z. Yeah, that is applied in the AOB area, AN minus, what else is on aligned with the z-axis? Yeah, tau xz times a. This is applied on the ZOB area, and this can be AL minus, and the other one is, yeah, tau, this one here, tau yz, that is now aligned in the other plane, or sorry, is applied on the other plane, equals 0. Then if I rewrite these according to the other two, the XY axis, and then following the same sequence LMN, I will end up with this thing here. This is going to be tau z. And again, I can get rid of the areas here because I definitely have an area. dz minus, nope, this one, who comes, yeah, tau xz L minus tau yz m minus sigma zz n equal to 0. Now, this is important to mention. This equation, and this equation are what is called the Cauchy stress formula. Stress formulas. And actually, to better see it, we could write this equation, these Cauchy stress formulas in matrix form. And that's going to be something like this. On one vector, I'm going to collect, in one vector, I will collect what is the T stress. That's going to be, or T, yeah, T stress. It's going to be Tx, Ty, and Tz. Even though, again, it's important to mention, even though we use forces for our equilibrium, let's say, operation, we end up just working with stresses, and that's what we wanted. Minus, then I'm going to open up here and check this out. This is going to be something that you're going to be seeing very often from now on. And this is something you need to get used to. I'm going to have a matrix here that is going to be represented by the following terms. Sigma xx, here is going to be tau xy, tau xz, tau yx, tau zx, sigma yy, tau, following the same, it would be zy, yes, tau yz, sigma zz, and then this has to be, or it's going to be multiplied by L, a vector m, and this is equal to 0. This equation here is the matrix representation of what we have here. And as I mentioned, that you're going to be seeing this very often from now on. This specific matrix here is what is called the stress tensor. Stress tensor is constant in all. Under the assumption we started this course, this stress tensor is not going to change. It's going to be also equal in every, let's say, in every point of the body. And what we have here is that if we want to transform from one, basically we're going to see in the future, or in the following, what I'm going to write next, that if I want to know what's the stress in a different plane, by using the direction cosines and the stress tensor, I could transform this or map this stress tensor into a vector that's going to be, or it's going to represent that stress in that other plane there. And the inclination of that other plane is going to be represented by the different direction cosines. Okay, but we haven't answered what's the value of the vector. Where was it? we have an answer. What's the value of this, the vector, or what's the value of the stress in the normal direction to the inclined plane and in the tangential direction of the inclined plane. Let me try it again to have it here. I'm going to have the unit vector and this other unit vector. I will have the vector that we are working with that was represented firstly in the Cartesian coordinate system. And the whole idea is to know how much is this normal stress, because I'm considering that this is a stress. But again, it can be any vector. And what's this shear stress? I know that this is the normal stress. I know that the normal stress is going to be the projection of this t vector onto the unit vector n. And that's easily represented by using the scalar product of two vectors. This is going to give me this representation. Then I know that, well, having that n is equal to a vector represented by L, M, and N transpose, and T being a vector represented by Tx, Ty, and Tz, that sigma, or the normal vector, is going to be equal to this. It's very simple. Yeah. Now, to know how much is the stress in the normal plane or oriented to the normal plane, what I need to do is to multiply the results of each one of these components of the vector or stress T with the L, M, N, which are the direction cosines. Let's do it. So we'll have that, we'll read that down here, that sigma n is equal to Tx, but I know that Tx is represented by all of this. Again, Ty is going to be represented by all of these, and Tz is going to be represented by this. Then sigma n is going to be equal to Tx, and actually I can see it from this matrix here. Is enough. It's going to be this times L. Yeah, to open parentheses here. It's going to be sigma x times L plus tau x yx times m, yeah, plus tau zx times n, and that's going to be multiplied by L, plus tyy, which is represented by this second row here. This is tx, tz. Then it's going to be, need to see this matrix here. It's going to be tau xy times L plus sigma yy times m plus tau zy times n. This is times m. Okay, we'll have to write it down here. Plus tz, again, this one here. It's going to be tau xz times L plus tau yz times m plus sigma z times n, and this is going to be multiplied by n. Perfect. I'm going to simplify this equation here so we can arrange terms. N is going to be equal to sigma x L squared plus tau y x m, write it in order, lm plus tau, many mistakes, tau z x m l plus tau x y l m plus sigma y y m square plus tau c y m n. Yeah, it's going to make a change here, invert these terms because I want to have them in the order that I have written the direction cosines ln. Yeah. Plus tau z dot tau x z ln plus tau y z m n plus sigma z t n square. Yeah. As I mentioned, I'm going to arrange the terms. I'm going to take these ones, the normal stresses, this one, and this one first. I will have sigma xxl square plus sigma yy m square plus sigma zn square. Then let's check the other terms. Tau yx, this one here, and this one here. Taking advantage of the reciprocity of shear stresses, I can do this. Plus 2 times tau xy lm. Similarly, I can do the same with zx and xc. Plus 2 times tau xz ln plus, finally, 2 times tau yz mn. And if you want to know what's the stress represented on an inclined plane in the normal direction, here you got it. What's the value of the shear stress of the tangential stress in the plane? As I mentioned before, we know that t squares equals to the normal stress square plus this shear stress square. Let's put it in this way. I want to know how much is this one. So by having the normal stress now in terms of the stress tensor quantities, I can know how much is this tau here because I can do just the simple subtraction. In this way, you can find a Cartesian vector. Let's call it in this way, a Cartesian vector which is represented in my x, y, z Cartesian coordinate system, represented in another on an inclined plane with components or oriented with the components of the normal component to the plane and the tangential component to the plane. And this is where you can kind of transform from a Cartesian coordinate vector to an inclined coordinate vector. Yeah, we'll stop the video now. And in the next video, I believe it's going to be one of maybe the last one. I'm not sure, but I will talk about what happens when I find a plane like this, an oriented plane, which doesn't have, or when I represent the stress on that plane it results, or it turns out that there is only a normal component, or the vector is completely aligned with the normal component to the plane, and there are no tangential components. That's what is called principal stresses. And we will see that in the next video. All right, well, thanks for watching.